Hello, this is Rafael Banag. This is the second question of the CALENG2 project. This question is, two identical semicircular windows are placed at the same depth in the vertical wall of an aquarium. Which is subjective to the greater fluid force? Explain. So before we go into the explanation, we need to understand this. The deeper something is in water, the more force it's subjected to. That's because of all the water compounding itself onto the object. So this is the equation that we are going to use. This is the fluid force equation. W is the weight density of the liquid. Function h is how deep the part of the shape is. And function L is the length of the part of the shape. So how we solve fluid force equations if it's on a vertical plane is that we're going to scan from top to bottom the shape. So imagine this shape underwater on a vertical plane, and imagine this brown rectangle. So we're going to get how deep the part of the shape is at the brown rectangle and how long it is, how deep it is here, how long it is here, how deep it is here, how long it is here, all the way down to the bottom. So we're essentially just scanning from top to bottom and calculating it. That is what this equation is doing with the integration. So we can move on to the written equation. So over here we have the fluid force equation, and here is the scenario. W is a constant since it's outside of the integration. So that means we can just plug in the usual weight density of water. The weight density of water is usually 9,800 newtons per meter squared, or 62.4 pounds per square feet. We can just plug that in. For how deep the part of the shape is, or the function of h, we have d plus y. D is how far the top of the shape is to the surface of the water, and y is how deep this brown rectangle is here from the top of the shape. And for how long the shape is, we can just get the x value of the shape of where it currently is and times it by 2, because x is only just half the shape. So we can say that x is the radius, since it's half the length of the diameter of the circle. So we can just say that it's just r. However, we can't plug this into the equation because it has x. We're using y for this equation. So we need to make this equation have y in it. One way to do that is to just make this equal to y, the x equal to y. So in order to do that, we turn to the equation of the semicircle. X squared plus y squared equals r squared. Equal to x is x squared equals square root of r squared minus y squared. Replace the x there with this thing we have here and plug it into the equation. It's that simple. Step 2, we are going to get the integral of the equation here. First, we need to plug in our values. Since we already have the constant of the weight density of water, we can just plug that in. Since we're using meters here, we're going to use 9,800. However, d is not defined, so we're going to make our own little scenario here. D is 10 and the radius is 6. Plug that into the equation. Here we have two parentheses that are multiplying each other. That means we need integration by parts. Then we get this. We have two integrals here. First, we'll deal with this section here. So we'll bring it down here. It has a square root and it has two values that are squared. So that means we can use trigonometric substitution. Y becomes 6 squared sine squared theta. And then we can simplify that further until we get 6 cosine theta. Now we need to turn derivative of y into derivative theta. Here we take the substitute. Y is equal to 6 sine theta. So dy is 6 cosine theta, derivative of theta. So we're just going to plug that into the equation. On the next slide here. Now we have 6 cosine theta times 6 cosine theta, derivative of theta. Remove the constants. 6 times 6, 36, times 20, 720. Now we times the cosine together, and now we have cosine squared, derivative of theta squared. Now we're going to get the integral of that. It becomes 720 times cosine theta times sine theta over 2 plus 1/2 and the integral of derivative of u. So we can simplify this further by using the reduction formula. Basically, we're going to use this formula to find out what we should replace theta with. We should replace theta with arcsine y over 6, according to the reduction formula. Plug that into the equation, cosine arcsine y over 6, etc., etc. Simplify that further down to this one. 720 times square root of 1 minus y squared, etc., etc. Then we can simplify that further by dividing 720 by 6, and it becomes 120 times y. That's the simplest form we can make it. Now on to the second part of the equation that we have earlier. This is simple because we can just use u substitution. U is equal to 6 squared minus y squared. Use this power rule to get the integral of square root of u, and then we just plug u back into it, and we have this equation. So now we can solve for the hydrostatic fluid force. A while ago we saw that there are limits. These limits are the top and the bottom of the shape. They have to correspond to the shape. So it's a circle, that means the origin of the circle must be the center, so it's 0. So from 6 to 0, we're going to integrate from 6 to 0. So we're just going to plug those values in, and then we get 6.95 times 10 raised to 6 newtons of force. For Windows 2, it's just Windows 1 upside down, but since the origin of the circle has to be 0, it's 0 to 6, to negative 6. We're finding the integration from 0 to negative 6. So plugging those values in and doing the math, we end up with 4.13 times 10 raised to 6 newtons of force. As you notice, Windows 1 has more force than Windows 2. Remember what I said earlier. The deeper something is, the more force it's subjected to. The mass of the area here of Windows 1, more of it is at the bottom. It's deeper. However, in Windows 2, a huge part of the mass is at the top, which means that a lot of the force here is strong, but there's not much area in Windows 2 to get all that force. In Windows 1, it's just this big massive area here that takes up all the force. So that's why Windows 1 is subjected to much more greater fluid force. Thank you for listening. I hope you understood why we use integration for fluid force and what we do and why we use the integration force. It's because we need to make sure that we have accurate results the deeper the shape is into the pond. Thank you for listening, and be safe. So this problem comes with a list of commonly asked questions. The first question is, why does fluid force require integration if it's on a vertical plane? This is because the deeper something gets into the water, the more pressure there is, the more pressure builds up. That means there's more force. So the topmost part of the window here has the least amount of force, and the bottommost part has the most amount of force. And since it's on a vertical plane, it varies. And the only way to add all these varying forces is through integration by limits. The second and third question is, why are the limits of one window 6 to 0 and the other 0 to 6? And why is the function of h, or how deep the part of the shape is, equal to d plus y? So imagine this blue line is the water, and this circle is the windows that we're dealing with. When you're dealing with circles on the Cartesian plane, the center of the circle is usually the origin, or 0, 0. Notice how 5 goes to 0 and 0 goes to negative 5. That's window 1 and window 2. That's why the limit of one window is 6 to 0. That's because it's the top part of the circle. And 0 to negative 6 is the bottom part of the circle. And since we're compensating for the fact that the center of the circle is 0, 0, the function of h has to be d plus y. Usually for a regular shape, it would just be negative y. But since we're dealing with the center of the circle being the origin, it has to be d plus y.
Hello, my name is Jason Larios, and I will be going over problem number 99. Laplace transforms. Let f of t be a function defined for all positive values of t. The Laplace transform of f of t is defined by this integral, f of s. It is defined by this integral when the improper integral exists. Laplace transforms are used to solve differential equations. Find the Laplace transform if f of t is cosine a times t. So first of all, what is a Laplace transform? A Laplace transform is basically a way to simplify differential equations into algebraic equations. Okay, so on to solving this problem. The first step of this problem is to plug in f of t is equal to cosine at t. Plug that into the equation the integral we were given in the beginning, f of s. So from here, we get this equation. And now we just apply the formula of integration by parts. So to use this formula, first we have to set these variables. So we set u is equal to cosine a times t, and the derivative of u is equal to negative a sine a times t dt. And we also say that dv is equal to e to the negative st, and v, which is the integral of dv, v is equal to 1 over s e to the negative s times t. Now that we have all the variables, now that we have all the values, we simply plug them into the integration by parts formula. Doing that, we get this new equation. So from here, we can simplify this part, which is the uv part of the integration by parts formula, because it is no longer inside an integral, it is outside the integral. So solving this first, we plug in t equals 0, and up to t equals infinity, we plug those two values in, and we get the answer of 1 over s. Now we bring 1 over s down here. 1 over s, and then we also bring this from back here, we bring this other part of the equation down here. Get this equation. From here, we simply use integration by parts for a second time. Alright, so in order to use it a second time, we have to set the values for u, du, v, and dv. So we set u is equal to sine a times t, du is equal to a cosine a times t dt, and dv and v are the same as the first part of the problem we went over. So dv is simply e to the negative st, and v is equal to negative 1 over s e to the negative st. So plugging those into the formula of the integration by parts method, we get this new equation. So from here, we can simplify uv, which is this, by solving from t equals 0 to t equals infinity. And from that, we get 0. So now we bring 1 over s down here, and we bring this part of the equation down here, and we can just we don't need this part of the equation anymore because it's just equal to 0. So continuing from there, What we do next is we factor out, or we take out the constants from the integral. So since a is a constant and 1 over s and negative 1 over s is a constant, we take that out of the integral and we get a over s. We take out a over s from the integral. From here, we notice that this integral is the same as f of s from the beginning. Since it's the same, we can replace it with f of s. Now all we have to do is simplify this equation and we can get the final answer. So from here we isolate 1 over s to one side, and then so that we can factor out f of s. So from this side we factor out f of s. So f of s times 1 plus a squared over s squared is equal to 1 over s. So then we know that we replace 1 with s squared over s squared, so that we can add it to a squared over s squared. From that we get this, s squared plus a squared over s squared times f of s, which is equal to 1 over s. Now we divide both sides by s squared plus a squared over s squared, and we get f of s is equal to s squared over s times s squared plus a squared. And simplifying that, we divide s over s, which is just 1, and we get f of s is equal to s over s squared plus a squared, and that is the final answer. Hello, this is Jason Larios, and I'll be going over this problem about bounded surfaces and multiple integrals. Now this problem asks to calculate the volume between the paraboloids z sub 1 equals x squared plus y squared, and z sub 2 is equal to 1 over 3 times 4 minus x squared plus y squared. Now essentially, if we graph this, we get this sort of parabolic and circular object. We want to find the volume of this region. Okay, now the first thing we want to do is look at this disk underneath. We know that it has a radius of 1, this object, and we know it's circular, so we can say that disk D is equal to x squared plus y squared equals 1. Now, an easier way of looking at this is this small graph over here. Here it shows, from a higher cross-view perspective, it shows a circle with radius 1. Now we'll be coming back to this later to help us visualize, to find the limits of the double integrals. Now to start finding the volume of this volume of this region, we want to start by creating a double integral. And since we're finding the volume in between these two paraboloid equations, we want to subtract the first equation from the second equation. So with that we get the double integral of z sub 2 minus z sub 1 dA, derivative of the area. Now we simply plug in the values, or the equations, into the variables. We plug those in and we simplify. Now simplifying, we go down here and we get the double integral of 4 over 3 times 1 minus x squared plus y squared dA. Now from here, we want to replace dA with r dr d theta, because we are no longer looking at this problem of this integration as horizontal and vertical lines. We are looking at this as parabolic and circular. So we can kind of visualize this as if we're looking at a spider web, for example. in the spider web, there are a lot of tiny rectangular arcs that if you add all of these rectangular arcs up, you can get the area of this spider web. So we can replace dA with r d theta because we are doing that. And we can also replace x squared plus y squared with r squared, because x squared plus y squared is equal to r squared. Now replacing that, next we need to find the limits of the double integral. So to find these limits, we want to go back to this disk. Now we want to find the polars, which are essentially the limits of the double integrals. So the polar with respect to r is simply 0 to 1 because it's 0 to radius 1. Now the polar with respect to theta is 0 degrees to 360 degrees, which is also 0 to 2 pi, which we will be using. Okay, so since we are integrating with respect to r first, we want to put the limits of r, which are 0 to 1, here. And since we're integrating with respect to theta next, we want to put the limits of theta, or the polars of theta, excuse me, which are 0 to 2 pi. Next, we can go on to the next line. So all we do now is multiply what's inside the brackets by r. Multiplying that, we get r minus r cubed. Now we integrate r minus r cubed. We integrate that and we integrate that with respect to dr. Integrating that, we get r squared over 2 minus r to the 4 over 4 from 0 to 1. Solving that, we get 1 over 4. Now we can bring 1 over 4 back into the equation. Now integrating with respect to theta, we get 1 over 4 theta from 0 to 2 pi. And solving that, we get 1 over 2 pi. Now all we simply have to do is multiply 4 over 3 times 1 over 2 pi. And here we get the final answer, which is 2 over 3 pi units cubed. So that is the final answer to this problem. Hello, so here are some common questions on problem number 3. So what is z? Z is a variable, just like x and y. Though sometimes people may get confused that z has a certain specific value. Question number 2. In calculating the integral in problem number 3, why is the integrand z sub 2 minus z sub 1 and not z sub 1 minus z sub 2? So looking at this graph, this top parabolic curve is z sub 2, its bottom parabolic curve is z sub 1. If we were to use z sub 1 minus z sub 2, we would be getting a negative volume. And so that would be wrong. So we would want to use the bigger number minus the smaller, or the bigger volume minus the smaller volume to find the volume in between the two. Alright, so why is the polar 0 to 1 and not negative 1 to 1 when finding the polar with respect to r? So to find the polar of this disk, we must start from the center, which is 0, and the range is the center to the radius, outer radius. So it would be 0 to 1 and not negative 1 to 1. Okay, so also, what are some applications of multiple integrals? Multiple integrals is mostly used in the studies of physics and engineering, as they use multiple integrals to find the measurements of the volumes of the materials you're using. That is very important in physics and engineering.